All right. So here we are again, and in the previous class, I was discussing with you the very fundamental aspects of coordination chemistry. What is a metal complex? What is the terminology, right? And then I briefly also I discussed with you uh, that what was the work done by Werner and how he was able to give some very preliminary information about the metal complexes. Okay, and after that, we were able to also understand a bit information about the geometry and number of bonds, and maybe a little bit about the shape, especially in case of the octahedral geometry. However, still, most of the properties uh, and the interesting properties of transition metal complexes remain unexplained by using Werner's theory. So we are here again, as I told you that let's study first the valency bond theory. Valency bond theory was a very important development in the bonding theories. Okay, whether it is given for the simple complexes or for the transition metal complexes, right? So as in the the valency bond theory for the simple compounds, the simple organic compounds, right? Uh, what do we consider? Basically, the concept of the sigma bonding, pi bonding, resonance, hybridization. All these concepts we study in the valency bond theory, right? In the valency bond theory, the most important that postulate was that a electron is donated by both the bond forming atoms, right? And let's say there is a bond between carbon and carbon, one electron will be donated by each carbon to form a bond, covalent bond between them. So obviously that was not, that is not the case in case of transition metal complexes, as far as the ligand and metal bonding is concerned. So this theory was modified. Okay. So here, as it was modified, that the basic idea of the theory is that the formation of a complex is a reaction between a Lewis base, that is ligand or electron donor, and a Lewis acid, that is metal or metal ion, that is electron acceptor in this case. And in this case, because both the electrons of the bond are donated by the ligand, right? They are not shared equally. They are donated by the ligand. So this bond was called as coordinate covalent bond or dative bond, okay, between the ligand and the metal. This is based on the following assumptions. So what are the assumptions in the valency bond theory? Uh, the central metal atom or ion provides number of vacant sp or d orbitals equal to its coordination number to form coordinate bond with the ligand orbitals, right? So let's say, for example, if you octahedral complex and you need to form six bonds, so six vacant orbitals has to be provided by the metal atom. In those six orbitals, six ligands can dominate their lone pairs, right? So whatever the coordination number, that many orbitals has to be provided by the central metal. Then each ligand has at least one sigma orbital containing a lone pair of metal. Then only it is a ligand, right? The empty orbitals of the metal atom or ion then undergo hybridization to form same number of hybrid orbitals. Okay. So this is the concept that we will be discussing in the next slide also. Um, the hybrid orbitals overlap with the filled sigma orbitals of the ligands to form ligand to the metal coordinate bond. Fine. The geometry of the complex depend on the hybridization of the metal orbital. Right? Whatever the hybridization, depending on that, and that will be geometry. I'll come to that. Just wanted to make you little clear on this concept of hybridization. Like for example, methane is the most easiest and first example generally that is discussed when we discuss hybridization. So what happens in case of methane formation? This is normal complex. So there is a carbon having the configuration 1s2, 2s2, 2px1, 2p1. Right? So it has only two unpaired electrons. So in this case, if the configuration looks like this, you expect that carbon should form only two bonds. Okay, however, carbon in most of its compounds, except just the carbenes, most of the compounds, it is tetravalent, right? So what happens that in general we explain this that one electron is excited from 2s to 2p. So effectively there are four unpaired electrons. Then these four unpaired electrons they undergo hybridization to have four sp3 hybrid orbitals, each having one electron, and then four hydrogens will come and they will share the electron in these orbitals. So four bonds will form, and sp3 hybridization will be overlapped, right? That is exactly how we explain this, right? However, at this point in the master's level, it is important for you to remember that hybridized state they actually never exist. Okay, actually they don't. Okay, what does that mean? That means if somebody asks you like, who will ask carbon that okay, four hydrogens are coming soon, so you please excite this electron quickly to this and have four unpaired electrons. Like nobody is there to tell carbon that. In that first pole, of course, one or two bond will form, some energy will be released, that energy will be utilized to, excite this electron from here to here. So it's a game of energy basically, right? After two bonds are formed, then two more bonds can be formed. However, if you see carbon, one s orbital and three p orbital. S orbital is spherical, three p orbitals are at right angle to each other at 90 degrees. So the four bond if formed like this, that will be very unstable arrangement because the electronic repulsion will not be allowing this geometry, right? One linear bond and three bonds at right at 90 degree. That will not be energetically that will not be favorable. So what will happen? Immediately CH4 molecule will relax to the least energetic form, that is what is the tetrahedral form. In tetrahedral, the bonds are as far apart as possible. Okay, so this is the game of the energy. However, this is easier to explain it in this way that hybridization occurs and then the geometry forms. Okay, that's what in the Valence bond theory also. If there is sp hybridization, the geometry will be linear. If it is sp2, then it is triangular planar. If it is sp3, then tetrahedral, so on and so forth. If it is d2 sp3, it is octahedral. There is another one that we will study, sp3d2 outer orbital are used, right? That is also octahedral, only the properties will be different, right? DSP2 for square planar, DSP3 for triangle biplanar. So only thing is, you can see whether if you know the geometry, then you can tell that in this case, we need to have sufficient number of orbitals to have this kind of hybridization, right? And you can explain the bonding property. Only thing is, um, you need to know some properties. It is usually possible to predict the geometry of a complex from the knowledge of its magnetic behavior on the basis of Valence bond theory. So we need to have magnetic behavior, knowledge of magnetic behavior and the geometry. Then we can tell this is the hybridization and this is the bonding model as per the Valence bond theory. Okay, so let's take some example. Okay, the first example, there is generally discussed actually is cobalt hexamine. Before we discuss cobalt hexamine, we need to know what we need to explain first of all. So read it carefully. In the diamagnetic octahedral complex, lot of information given here. It is diamagnetic. Diamagnetic means there are no unpaired electrons in the complex after it is formed. And the geometry is octahedral. These informations are given to you. And then you have to make a bonding model out of this information. And the cobalt is in plus 3 oxidation state, right? So the electronic configuration is 3d6. If you arrange the box diagram of 3d6, then you know that you have to put 5 electron first and 6 electron will be paired up in this orbit. So effectively you have 4 unpaired electrons. But we know, right, we know that there is no unpaired electron in the actual after the complex is formed. So what is suggested that in order to have, this is the geometry is octahedral, and in this case no unpaired electron, so these two electrons let us pair with them, and only three orbitals are enough to put these six electrons, right? So now these two orbitals 4s and 4p they are available to form a or undergo a d2sp3 hybridization, as simple as that, right? So in the case of cobalt hexamine, these six electrons are paired up here, then the rest of the six orbitals will be used for the donation of the lone pairs of electron from the ammonia molecule, so they are also full now. Good. Now, if you look at this model, it's explain all the property. Octahedral, yes. Dimagnetic, yes. Cobalt 3 plus, yes. Right? Everything is explained for this complex. So, only thing is we knew the magnetic property before. Right? We knew what to explain, so we made a model. Alright, now you can see another molecule, another cobalt complex, the cobalt hexafluoro 3 minus complex. Again, this is given that it is a paramagnetic octahedral. Paramagnetic is there, octahedral, right? And this is also 3 plus, cobalt 3 plus, so D6. So in this case, since we know it is paramagnetic, no need to pair the electrons, right? We have to find out 6 orbitals other than these orbitals because this is paramagnetic octahedral. So yes, these are 4s orbital, then 4p. So 3 and 1, 4. And 2 orbitals you can take from the 4d, outer. In the previous case, it was inner orbital. This is the outer orbital. And so you can use this 3d, and sorry, this sp3d2 hybridization will be there. Okay, this is sp3d3 written, it's wrong, sp3d2. Okay, that will be hybridization. Take the 6 uh, orbitals, enough for forming the octahedral complex. Again, it's paramagnetic with 4 unpaired electron, right? It's octahedral. Now, again, it is explained. Only thing is, when we were explaining it, we knew that what is the magnetic property and what is the geometry. Then only we could explain. Okay, otherwise, we will be ending up giving couple of models, and you can say, okay, whichever is matching with the magnetic property, that is the right model. So this is also called as spin-free complex because the spin is not paired here, or high spin complex, or also called as outer orbital complex because outer orbitals are used. While the previous case, this is called as inner orbital complex because 2 of the inner 3d orbitals were utilized in the hybridization. Inner orbital complex or low spin complex, right? This or low spin complex, right? And that is what the names are given. All right, very easy. Only thing is you need to know the magnetic property. The octahedral complex of cobalt 3, right? It will be, if it is diamagnetic, you have to pair up, and 6, it will be having D2sp3 hybridization. If it is paramagnetic and octahedral, then you can say it is sp3d2 hybridization. That is what we have seen in this case. In case of, let's say, a D8 system of platinum Cl4 2 minus, okay, it's diamagnetic. You know it before. Diamagnetic, very good. If it is diamagnetic, right, it is D8 system. So what you will do, you write the box diagram and you last 2 electrons, you just pair. D8, if it is paramagnetic, then you don't have to pair up like nickel Cl4 2 minus. You don't have to pair up these electrons because NiCl4 2 minus is known, it's paramagnetic. Right? So depending on the magnetic property, accordingly you make the bonding model. That is how this theory is. Okay, that you can explain the magnetic property, you can explain the geometry, you can explain the hybridization, right? Very good. Okay, NiCl4, as I told you, again you can see that 2 electrons you don't have to pair, right? It's tetrahedral. It's tetrahedral, so you need only 3 orbitals to make the 4 bonds. Sorry, 4 orbitals to make the 4 bond. That is 1s and 3p. So hybridization is sp3 over here. However, in this case, platinum Cl4, it is square planar. So 1d, 1s, and 2p. So dsp2 is the hybridization. Right? No issue. So sp3 hybridized orbitals of nickel 2 will be like this. Or all chlorides can donate electrons over here. And NiCl4 remains paramagnetic and outer orbital complex. It is a high spin complex. All right. NiCl4, just one second, you can see NiCl4 because it is known that it is square planar and it is diamagnetic, right? So in this case, again, you can write the D8 configuration, but you know that it's diamagnetic, so pair it up, pair the electrons here, and form a dsp2 hybridization, right? Each of the hybridized orbital receives a pair of electrons from the cyanide ion. The compound is diamagnetic as evident from the absence of unpaired electron. If you are asked a question that, okay, based on this valence bond theory model, explain the bonding model for this complex, this is how you should show the bonding, the box diagram, and then you can show what is the hybridization and how you explain the properties. It is important to note that hybrid orbitals do not actually exist. I told you this, right? In fact, hybridization is a mathematical manipulation of wave equation for the atomic orbitals involved. All right, it is just the mathematical manipulations, the wave equations. All right. So this is called, if you know the magnetic properties and you can explain the bonding model, then this is called the magnetic criterion of bond type. Right? You give me the magnetic property, I give you the bonding model. Right? It is called the magnetic criterion of bond types. Especially it was told for the D8 complexes. In a D8 complexes, if it is paramagnetic, it is square planar, dsp2. If it is it is paramagnetic, it is tetrahedral, sp3 hybridization. Okay. If it is diamagnetic, it's still tetrahedral. That is the case of NiCO4. But remember, in NiCO4, it is a D10 configuration. It is zero oxidation state of matter. NiCO4 is a metal is in zero oxidation state. All right. So this is D10 configuration, and that's why all electrons are now paired up into the 5d orbitals, right? So making it diamagnetic in that way. Okay. NiCN4, I told you it's D8 system, diamagnetic, has to be dsp2. NiCl4, tetrahedral, paramagnetic, right? Two unpaired electron. This is an interesting example. Copper tetramine 2 plus. Copper tetramine 2 plus is interesting because it is known that copper, you know, so copper here is what? Copper is in D9 configuration because it is copper 2 plus, right? And if it is D9, right, it is also known that it has a square planar geometry. Square planar geometry. Okay. If it is having a square planar geometry, then how do you explain? Okay. So in this case, basically, if you have 9 electrons, okay, 9 electrons will be occupying all 5d orbitals, right? So you have only one unpaired electron in one of the d orbitals. Okay. So you cannot have a dsp2 configuration that is required for the square planar geometry, right? You can't have a dsp2 because inner d orbital is not available, right? So when people say that why don't you excite that one electron to the outer 4d orbital? Okay, one electron from 3d to 4d, and then you have and then you can have sp sp dsp2. However, if you are putting one electron outside into 4d orbital, then oxidation of this compound should be very easy because you are having electron just like say sodium. Sodium is easily given that electron to go to sodium plus because nobody likes to have a single electron in the outermost shell. However, that is not the case. Oxidation of copper 2 complexes, copper 2 plus complexes is very difficult. Very difficult. So what is proposed is that you can't move that electron from 3d to 4d. However, since for the formation of a square planar geometry, you need one s, you need 2p and one d. So this d orbital will be coming from utilizing the one 4d orbital. Okay, so that is how you can explain sometimes when looking at the properties of a compound, you can explain. You have to see carefully what is the experimental data you have. Based on that only you can use any of the theory, whether it is whichever, even molecular orbital theory or crystal theory. You need to see what you are explaining, what you need to explain. I told you copper 2 complex not very easy to oxidize. Then only you can propose a sp2d hybridization. All right. So that is all about the valence bond theory, that you know some properties, you use the box diagram, and then you make available that many number of orbitals as required from the geometry, and then you can explain it based on the Valence bond theory. So now, if you see carefully, if you summarize this Valence bond theory over here, that have you understood geometry? Yes, to some extent. We understood geometry because scapular, tetrahedral, right, octahedral, all the geometry are taken care. If the hybridization is known, then you can explain the geometry. Number of bond and shape also, that is related, and you can explain. Magnetic property to some extent, yes. However, if the complex magnetic properties are there, then we cannot explain by this theory. Okay, high spin and low spin nature, yes, that also is explained. So magnetic property are explained to some extent by Valence bond theory. Maybe the complex magnetic behavior like anti-ferromagnetic coupling or ferromagnetic coupling, those kind of things you cannot explain with the Valence bond theory. Still, there are many properties like color, spectra, structure, stability, reactivity, splitting the orbital, effect of ligand type. These are the properties that we still, even after using the Valence bond theory, we really cannot understand. Okay, just by simply, let's say, for the color, you simply can't say whatever light is absorbed and the corresponding color will be there to explain the corresponding color. Okay, so that is very simple, but we know that sometimes the color of the same compound is different only just by changing the nature of the ligand. Why that happens? Sometimes there is one band in the spectra, sometimes there are two bands in the spectra. Those things need to be explained. It's much more complex than said in the Valence bond theory, right? So still there are a lot of things that we need to understand. So you need another theory, right? So a lot of limitations are there for the Valence bond theory. It fails to predict whether a four-coordinate complex will be tetrahedral or square-planar, and whether an octahedral complex will low spin or high spin. Only that by knowing the magnetic property you can explain. Distinguish between certain geometry like tetrahedral or distorted. Distorts they don't explain that. Right? That's why I'm saying that geometry can explain to some extent, but if let's say there's a distortion, you cannot explain by nature, right? And of course, other things that I told you that these reactivity, stability, they are not explained. And also, like say, it does not adequately explain the magnetic data beyond specifying number of unpaired electron. That only, number of unpaired electron only. Other than that, it will not explain. Too much stress has been given on metal ion, while the importance of the ligand is not properly addressed, right? In a system, and ligands are there, right? So many ligands are there. Metal is also there. Just by looking at the metal and its orbital, you can't explain all the properties. All the ligand should be also included. Okay, and because of that, of course, the Valence bond theory cannot be utilized beyond a certain extent. What is the next theory? Next theory is crystal field theory. Next is crystal field theory. Crystal field theory is, largely it explained most of the properties of tungsten metal complexes. So this theory we need to study in a more details than the previous two, Werner's theory and Valence bond. Okay, so this theory largely replaced Valence bond theory for interpreting the chemistry of coordination compounds. It was proposed by the physicist Hans Bethe in 1929. Subsequent modification was proposed by J.H. Van Black in 1935, and that is called as ligand field theory. Okay, that is basically also called as molecular orbital theory, but that we will discuss separately. Okay, this is the original paper of this. The Belhausen and wrote this Journal of Chemical Education. You can download, or university allow to download it. Journal of Chemical Education, 1979, original paper of crystal field theory. Okay, so that is how we are going to go about uh, this class. Okay, crystal field theory. To understand crystal field theory, we need to understand the d orbitals, shape of the d orbitals properly. Okay, there are, as you know, there are 5D orbitals. Okay, 5D orbitals. In fact, there are six. If you write, you can write actually the six wave functions for the d orbitals. But as we all know, the dz square is a combination of the two orbitals. That is dz square minus x square and dz square minus y square. If you combine, if you make a linear combination of the two, you get this dz square. In actual representation is d2z square minus x square minus y square. And since this the symmetry in the xy plane is easily represented by this the donut type of the structure, right? So this is plus sign here, minus sign here. Remember that d orbitals, they are having, like, unlike the p orbital, in the p orbital the opposite lobes are having opposite sign, one is plus, one is minus. Okay, in the d orbitals they are called girardi. Girardi means basically symmetry, plus this side, plus this side. Okay, minus this side, minus this side, plus plus, minus minus, they are symmetric. P orbitals are ungirardi. Okay, that kind of terminology, there are symmetry terms that we'll be utilizing, we'll be using those terms in our next discussion. Dx square minus y square and dz square, their lobes are along the axis. Along the axis. Okay. Like dx square minus y square has lobes around x and y axis. Okay. While the other three orbitals, dyz, dxz, and dxy, these are having their lobes in between the axes. There are three axes, x, y, z. Their lobes are in between the axes, right? So this is how the all 5D orbitals looks different. All right. So remember, if the ligands are approaching, okay, depending on which side ligands are approaching along the axis, they are going to affect these two orbitals more. If they are approaching in between the axis, they are going to affect these more, right? So this is how, based on this, the energy of the 5D orbitals in different geometry will be different, depending on the interaction from which side orbitals are facing the ligands. Depending on that, whichever is close or directly facing, that energy will be high. Other orbitals which are not facing ligands directly, their energy will be low. Right? So in that case, there will be a splitting of the orbitals will take place. Alright. So you can see that main assumptions of crystal field theory are over here. The interaction between the metal ions and the ligands are purely electrostatic. They are purely electrostatic interaction. The ligands are regarded as point charges. Okay. If the ligands is negatively charged, then ion-ion interaction. If the ligands is neutral, then ion-dipole interaction. Like, for example, ammonia, water, right? These are ion-dipole interaction. If, like, say, hydroxide ion or cyanide ion or chlorobromide iodide, they will have the ion-ion interaction, right? This theory, remember that this theory was developed for the crystals, like, say, sodium chloride structure, like that. That is why it is also known as crystal field theory. Okay, so obviously this, since it was developed for the crystals which are mainly the ionic compounds, so most of the assumptions are, so you see, most of the assumptions are related to the ionic bonding, which we know that is not true, but still this theory was able to explain the properties of transmetal complexes to a great extent, and it is still very, very relevant to explain the properties of transmetal complexes. Anyway, so electrons on the metals are under repulsive forces from those on the ligands, right? Whatever electrons are there on the d orbitals, okay, they will be facing repulsion from the electrons present on the ligands. The electrons on the metal occupy those d orbitals farthest away from the direction of the approach of the ligand, right? Electrons on the metal occupy those d orbitals which are farthest away, because they would like to minimize the repulsion from the ligand. So they would like to go as far as away from the ligand direction. Okay, and then whatever the resulting geometry is coming, that can be explained based on this splitting and based on this arrangement of the electrons on the metals and the what the repulsion they are facing from the ligands. All right, I think on that note, I will be, let me just stop this particular class over here, and in the next class we'll be discussing the crystal field theory in much more details. Okay, so thank you.